You will recall that the primary aims of air traffic service systems worldwide are to separate aircraft to prevent collisions, to organise the flow of traffic, and to provide support. Because radar technology is able to remotely identify aircraft and present this spatially to a controller, radar technology has now become a fundamental tool used by air traffic control to achieve its aim. Today, the use of radar, with the addition of computer-enhanced systems, is a completely integrated part of the control of air traffic. Before we look at radar technology in more detail, it is important to understand that an air traffic control radar system is not just a visible rotation dish seen near airports. A radar system will normally consist of a number of integrated systems, including radar sensors, radar data transmission lines, radar data processing units, and of course the radar data display. Radar systems are mainly being used to assist air traffic control whilst aircraft are airborne. But recently, radar is being extensively used as a ground movement monitoring and control system at the busier international airports. Such a radar system is called Surface Movement Radar, known as SMR. Advances in navigation, global positioning systems and automated flight controls have continuously improved pilot spatial awareness and has allowed for less restrictive separation standards being applied. This, in turn, has allowed the ATC system to handle more aeroplanes more safely and achieve a smoother and more expeditious flow of air traffic. Because air traffic control is responsible for separation of traffic operating under instrument flight rules, any air traffic control radar system must have a high degree of reliability, availability, and integrity. It almost goes without saying that because the system is so heavily relied upon, it must be backed up. Radar systems should not only display the position of an aircraft spatially, but also provide for the display of safety-related alerts and warnings, including confliction alert and prediction, minimum safe altitude warnings, and unintentionally duplicated secondary surveillance radar codes. In the modern commercial air transportation environment, radar has a vital role to play in the provision of air traffic services. The information that is displayed to a controller can be used to improve airspace utilization, reduce delays, provide more direct routings, and improve safety, facilitate the expeditious and efficient flow of departure traffic and its subsequent climb to cruising level, resolve potential air conflictions, provide flight vectors for expeditious and efficient approaches, assist pilots in their navigation, enable pilots to avoid extremes of weather, provide separation and maintain normal air traffic flow if an aircraft experiences a radio failure in a control area, monitor all air traffic. You may recall that there are two types of radar currently in use at most major aerodromes: primary surveillance radar, known as PSR, and secondary surveillance radar, known as SSR. They may be used separately or in combination with each other in the provision of a full air traffic control service. Although not strictly radar, but certainly an important method of surveillance, automatic dependent surveillance, ADS, is the future face of radar systems. Primary surveillance radar emits pulses of energy, some of which is reflected by the target back to the receiver. These targets can be objects other than aircraft. The radar return information is then processed and displayed on a screen, like the one shown. Secondary surveillance radar requires that the target aircraft have equipment on board to reply to signals sent from the base unit. These signals give more data to the radar return, like aircraft identification, altitude, and so on. Secondary surveillance radar is dealt with in more detail in another lesson. Although the purpose of primary or secondary cover, used individually or in unison, is to provide enhanced air traffic services to aircraft. This will include the provision of separation between aircraft. The information available to a controller from radar-derived sources will, as a minimum, include continuously updated radar position indications, radar map information, SSR returns in Mode A, a simple acknowledgement return, Mode C, an acknowledgement return with height information, and the new Mode S return, which will encode a unique identifier. However, radar position indications may be displayed in several ways. Radar positions can be displayed using radar position symbols, RPS, which we will examine shortly, primary surveillance radar blips, or secondary surveillance radar responses. On-screen radar position symbols may be displayed as primary surveillance radar symbols, secondary surveillance radar symbols, a combination of PSR and SSR symbols. Primary surveillance radar returns, secondary surveillance radar responses, secondary surveillance radar codes, and radar labels are also shown, along with unintentionally duplicated secondary surveillance radar codes. Track and predicted track data will also be available. Unless dictated by the circumstances of an emergency, direct pilot-controller communications are to be maintained throughout the provision of a radar service. This may be by voice, RTF, or by data link, the so-called Controller-Pilot Data Link Communications, CPDLC. Operating on their own discrete frequencies, the call signs used by air traffic controllers may or may not indicate the degree of control they exercise or the means by which any control is achieved. Typically, radar controllers are called radar, director, or zone, but other call sign prefixes may be encountered. You will remember that secondary surveillance radar equipment allows for the specific identification of aircraft by the employment of ground and aircraft-based equipment. Modern systems also provide for altitude information to be available, and the latest systems additionally assign unique identification codes to individual aircraft. This is called code conversions. Secondary surveillance radar use has its own standard procedures and phraseology. You have already learnt that some SSR codes are specifically assigned to particular circumstances. You will remember 7700 signifying an emergency, 7600 signifying communications failure, and 7500 signifying unlawful interference. But there are also other codes that are state-specific. These will be registered in the regional air navigation agreements of countries, and their use will be compatible with other adjacent states. Any SSR code changes will be kept to a minimum to reduce pilot and controller workload. Where necessary, individual aircraft identification codes can be issued, for example to humanitarian relief, medical or VVIP flights. When Mode Charlie, the altitude reporting element of an SSR system, is used, it must conform to a tolerance of plus or minus 300 feet. However, when reduced separation between aircraft is in force, the tolerance of the equipment is plus or minus 200 feet. To verify this accuracy, a controller will, upon initial contact, verify this, and if unable to do so, inform the aircraft to switch this Mode Charlie element of its equipment off. There are some rules and procedures that define when an aircraft can be at or assigned to, an altitude which is based upon the accuracy of the transponder. A particular level is deemed to be occupied when the aircraft is within a height bracket of plus or minus 300 feet of that flight level. An aircraft is deemed to be maintaining a flight level when Mode C derived flight level information indicates that it is within plus or minus 300 feet of the assigned level. When cleared to vacator level, an aircraft that has a Mode C derived indication of more than 300 feet in the anticipated direction of change is deemed to be vacating it. An aircraft climbing or descending is considered to have crossed a level when the Mode C derived information indicates that it has passed the level by more than 300 feet. Ground controllers will require confidence in the SSR accuracy of an aircraft, and aircraft will be considered to have reached a flight level to which it has been cleared when 3 consecutive renewals of the Mode C level derived information has indicated that the aircraft is within 300 feet of the assigned level. In this manner, all aircraft using a piece of airspace will be accurately tracked. This completes the lesson on general radar services.